Hello! Have you ever not been able to untie your shoelaces or maybe have to deal with this mess of knots? Well, that's what we're talking about today. Knots. More precisely, mathematical knots. Mathematical knots are different. You see, normal knots are tied but have open ends, whereas a math knot is one complete strip with no open ends. But before we do that, let's put down some base level questions we will be answering along the way. Knots, math, what makes knots different? How can we prove each knot is different, and why are knots so important? A knot is basically the embedment of a circle in 3D space, meaning that yes, a circle is a knot too, the simplest and most boring one, termed as a culprit knot, or as I like to call it, the imposter. What makes them great is that we can preserve all the information we have about a knot even after flattening it, helping us decomplicate them. But knots don't really stay the way they are. You can simplify them back to an unknot or their most simple state. You perform moves known as the Riedmeister moves. Like here, look at these. This one straightens out this loop, this one separates this intersection, and this one relocates strands under patterns. But once a knot is simplified, they can be identified by knot notation. But let's pause right there. To understand knot notation, you need to know how we identify knots. You see, when knots are flattened, you are able to see details like how many intersections they have and identify them by index notation. For example, there are 3 knots with 3 intersections, therefore indexing them as 1, 2, and 3. How do we know if 2 knots are the same? Well, that's ambient isotopy. Here our moves will help us find knot similarities. But what if the knots are different? So let's say our amazing moves don't work. Then we have to see if knots are tricolorable, which is basically the knot's ability to be completely colored by 3 colors, with rules obviously. But oh no, what if we see non-tricolorable knots that do not follow the color rules? Well, that's where our first piece of maths comes in, calculating the knot determinant. So look here what we need to do. We need A, find each crossing and then number them, and B, how many strands are there over crossings or alone. If rows is equal to the crossings and the columns is equal to the number of strands, then we can create a matrix, but with some rules. If the strand is under the crossing, it's a -1. If the strand is over the crossing, it's a 2, and if the strand does not meet the crossing, it's a 0. With that, we can delete a column and a row and find the determinant of the matrix, which, long story short, is basically the determinant of a 2x2 added into a formula for matrices bigger than a 2x2. The prime factors of this determinant are how many colors this knot can be colored with. Why are knots so important? Well, first of all, for biology, we know knots are the very shapes and how our DNA gets twisted and turned, helping us learn more about them. In statistical mechanics, entire 3D bodies can be represented in 2D space with the help of knots. Mathematical knots aren't just knots, they're literally what we're made of.